Hey, physics. All right, so this is the model practice and review slideshow here. The goal of this is to kind of bring it all together and give you an idea of like where we've come from and where we're going with this, okay? So the first thing that I want to do is talk about things that we know so far. So from investigation 1 and investigation 2, we know that objects can become positively or negatively charged. We know that charged objects have electrical fields that radiate outward or inward. We know that when electrical fields come into contact with each other, a force of attraction or repulsion is created. Remember, a force means movement, so that we can have a movement of coming together or a movement of pushing apart. We know that opposite charges attract and like charges repel. Charged objects and neutral objects attract. But there's some things we don't know much about yet, like why do objects become charged? What does that actually mean as far as like physically what's happening there? And also, how can charged objects and neutral objects be attracted to each other? Like what is the mechanism there specifically? We've kind of talked a little bit about negative charges moving, positive charges staying in place, but there's a lot more to learn there too. So we want to take it back 1,000 years, 2,000 years, 3,000 years, whatever, and we want to do a thought experiment. We want to think about things like the early scientists thought about it in order to find out how did we get, as a culture of knowledge, how did we get to this idea that there are atoms? You guys know that there are atoms. We know that there are molecules. How did we get to that point where we could think about that without microscopes, without any of that stuff? And actually, atoms are too small to be seen with microscopes. So that's it's still it's cool. Okay, so there's two competing philosophies here. We have the philosophy of the continuous model of matter and the philosophy of the particle model of matter. So the continuous model of matter is that if you cut something, you can cut something an infinite amount of times in half, and it's always going to be that same thing. So we can chop a piece of wood into the smallest pieces, and that smallest piece is still going to be wood. There's a couple implications there. One is that that then all matter is like a consistent fluid. It's all the same thing, right? It's all going to be the same size, because if you can cut it smaller and smaller, each of those pieces is going to be the very same size, right? They're all the same thing, so why would they need to be different sizes, right? They're only different sizes if you cut them differently, right? But then the other, so what you need to do here is draw a continuous model of matter, what it would look like if you zoomed in on an object. So if it was me here, I'm not going to draw this for you here, but what I might draw is, since you can be theoretical and metaphorical about this, I might just draw like a big star for my object here. And then I might draw a smaller star here. That's the same substance, right? Or I could draw like a log of wood here, and then like a small piece of wood over there. So the evidence for the continuous model of matter is that that's what it looks like to our eyes, right? Like, I have this computer on this chair on this desk right here, and the chair and the desk, they all look like a continuous thing, right? Like, that makes sense to me as somebody who doesn't know about microscopes and doesn't know about the smaller and smaller things that we can see. And again, atoms are actually submicroscopic. Like, we can't even see them with a microscope. Like, our eyes physically can't see them. They're that small. It's super cool. So then we have this other philosophy that was the particle model of matter. So the particle model of matter says that you can break things down smaller and smaller, but eventually those things are going to break into pieces that are not that same thing anymore. So instead of wood, we are going to have this is like the modern version of this. We're going to have carbon, hydrogen, oxygen, nitrogen, sulfur, whatever. We have these building blocks, right? We're getting into the idea of atoms. You guys have seen the table of the elements before. Those elements are the building blocks of everything. So we have found out as a culture of knowledge that the particle model of matter is the correct thing. I'll tell you what this picture is up here with Democritus thinking about these the steps that it took to get, obviously, like Democritus and back in 2,000 years ago, they weren't thinking about the table of the elements. That hadn't been developed yet. What they were thinking about is what they called elements, which were just like a few different things. It was like air, fire, water, and earth, and they combined in different ways. And that was kind of how they conceptualized the particle model of matter. But the theory had some good parts to it, right? And now that we know a lot more about what makes things up, we know what those parts really are. It's not fire, water, air. It's like carbon and hydrogen and oxygen and all that other good stuff that makes up the world. So now you're going to draw a model that explains what the particle model of matter would look like. So if this was me, I might draw, like I could draw ethanol because I know what ethanol looks like, right? I could also draw water. So maybe I could do this really easily. I would draw a cup of water in the object or substance here. And then I might draw a water molecule. And you guys have seen what a water molecule looks like a couple of times now. It's kind of a V shape or kind of a Mickey Mouse shape. It's got an oxygen atom and 2 hydrogen atoms attached to it. And the evidence for this, the particle model of matter, this is like the big ideas of this whole unit, right? Is that things can fit in between, like you have particles of different sizes, right? Like ethanol is a bigger particle than water. So water particles can fit in between ethanol particles. We also know that gas is made of particles also, and you can tell that that is a particle because it compresses, right? It doesn't compress all the way, it doesn't like go entirely away, but you can compress it, and those particles, those molecules will be closer together, right? There's empty space between them. In a continuous model of matter, there's not empty space between anything, okay? So I want you to get good at explaining what the answer to this question is. Will there ever be a point at which a piece of paper is no longer paper? Yeah, when you break it down far enough, you're going to break it into the building blocks of paper, which we now know are things like carbon, hydrogen, oxygen, all kinds of great stuff, right? So the next thing is the particle model of matter wins. We have an ethanol molecule here. We have a water molecule here showing the polarity of it, which is kind of a cool thing we'll learn about later. This is one conceptualization of what an atom looks like, and here's another one. So we'll get more into specifics on that later. But the particle model in liquids. So one way we found this out was that ethanol and water, the same amount of each one put together is going to add up to less than 2 times the whole. It's going to add up to about 1.8 because those water molecules, those water particles are smaller and they can fit in between the larger ethanol particles, just like rocks and sand in a jar. And you can see a picture of that here. You can see how it doesn't add up all the way because they filter in between each other. So here's your chance to draw a model that explains why 10 milliliters of water plus 10 milliliters of ethanol adds up to less than 20 milliliters of liquid. So for one of them, you're going to draw bigger particles, and the other one you're going to draw smaller, and they're going to like filter in between each other, just like this picture here, okay? So does the particle model also describe gases? Yeah, it does. Gas particles move much more quickly than liquid or solid particles. There's more space between them. We're going to learn a little bit about hydrogen bonds on Monday or Tuesday. The energy of the gas particles' movement is stronger than the attraction between the particles. There's actually, we've learned about, positive and negative charges. So each molecule, which has a few different atoms in it, has a little bit more of one charge in one place and another more of another charge in another place. And those charges kind of hold the things together. But gas molecules don't have much of a charge at all. They're really balanced between the 2 atoms that are stuck together. So they don't want to react with each other. So they just want to move. Like they've got a lot of movement energy, and they don't want to stick to anything else like water or like liquids or solids do, basically. So here we've got this model that shows why a full balloon is heavier than an empty one. Again, we're going to show particles here. This one over here has just a few particles of air in it. And remember that when we're talking about air and gas and matter, those are all similar things that we use the words different ways, right? So air is like anything, like all the stuff that's around us right now, all the stuff that we breathe in, just generally the stuff is air, right? But when we're talking about gases, that specifically is a phase of matter. So we can talk about water as a gas, water as a liquid, water as a solid, right? So a gas is just that phase of matter. And then matter itself is anything that takes up space and has mass, okay? So air has mass. It made that balloon heavier. You're going to draw a lot of little gas particles, air particles in there, okay? So then we have this video about compressing a gas, showing how this syringe works. I'm not going to do that for you right now because you can look at it yourself in your own slideshow. But what we're going to see here is that these two syringes have the same number of particles inside of them because they're stoppered. There's nothing going in or out. But in this one, the gas particles are going to be a lot more spread out than this one. And what this shows us is that those gas particles have a lot of space between them, so they can be compressed to some extent, right? So we're going to draw the gas particles and also the force arrows, because even though we can compress those gases in here, we're going to see a force that is pushing that syringe stopper or the syringe plunger back out, okay? So make sure you have a yellow force arrow pushing back out there. Okay, so then the last part of this investigation is making a good claim, evidence, and reasoning statement. This is how science is communicated to the public, is that here's this thing that we know, here's the evidence that we have for it, and here's the reason why that evidence supports our claim, right? So the claim here, the big claim that we are promoting in this investigation is that all materials are made of a collection of smaller particles that group or stick together, okay? So that is our claim. So we have some evidence for that. When we mixed water and ethanol, the total volume ended up less than we expected. We had kind of like a rocks and sand situation where the sand can fit in between the rocks. The water is the sand. The rocks are ethanol because ethanol is a bigger molecule. And the reasoning is that the particles must be microscopically different sizes that fit between each other, like rocks and sand. So we can't visually see the difference between ethanol and water and the sizes of particles there, but we can see that when they add together, they add up to less than it seems like they should. So again, our claim is that all materials are made of a collection of smaller particles that group or stick together. More evidence for that is that air can be compressed, right? So the reasoning of why that helps to further our argument is that there must be empty space between the particles. So our last slide here is just a question: which evidence is more compelling to you? Do you feel like the fitting between each other evidence is more compelling, or do you feel like the gas compressing is more compelling? Obviously, they're both good pieces of evidence. Which one do you feel like reaches out to you more, and why? Okay, that's it.